Hi there, this is Alan Brady with the first video of 3 to give you some guidance in attempting your final assignment. This video covers getting things started, doing the calculations associated with the horizontal curves, traversing and volumes, talks about different design priorities, and also gets you thinking about some of the instructions you might want to give your survey party. There are 2 other short videos that cover drawing the long section and then doing the vertical alignment design. To get started, hopefully you've already downloaded the PDF file from Canvas, which covers a Word question file and a plan, and then there's an answer Word file that you'll need to complete and submit as part of your assessment. So basically in this assignment, you're asked to do a preliminary design of the centre line for an access road to a rural property. Now this is the final assessment in the surveying subject. It's taking the place of a final exam. So we're only wanting to assess your knowledge of and your ability to do calculations for traversing horizontal and vertical curves, volumes, and that you can appreciate and work with contour plans. Please don't go running off trying to look at senior road design information or anything. Everything you need to know for this is contained in your surveying notes. Well, it's a real example. We're trying to actually give you something that lets you think like an engineer. We're going to get you to design a small access road. It might just be bulldozed through. It leaves a main road that you can see over in the left running roughly north-south. It's got to cross a creek and it's going to finish at a farmhouse. So you're going to do a preliminary design on paper for a road like this. Now the farmer's had discussions with you and he's marked out on the plan where the road has to go because he's got a particular point in the roadway where it's going to start from. It's got to cross a creek at a particular point and then dodge some trees, and then it's going to finish near the house. So there's a bit of flexibility. As you can see, it doesn't have a particular driveway or a boundary to worry about. So we can be a couple of metres either way at the end. But one thing he's important about is he's going to have a concrete slab built, and so the road must finish at a specific set RL. That is one of the most essential criteria in this road design. Okay, this is an example of the plan that you might see. The plan itself is the same as you got, but the lines drawn on it are totally different to anyone's version. So the red lines show the proposed route which you must adopt. It starts at Chainish North and it has 3 straights to take it through to the end. The blue lines mark a traverse that the survey party's done. They've come from A to Y to X and they've put a peg in that's going to be close to the end of the road. And the data for that traverse line are shown in your question file. You need to read that there. Now, you'll be given a specific RL to start your road at Chainish North, and that's where it meets Tuckers Road. But it may be that Tuckers Road is in cut or fill. So when you come to drawing your long section and you're drawing the natural surface, use the contours to get the natural surface, but remember that your road may start a little bit above or below that RL. The first thing you need to do is print a copy of your plan. Now we've drawn it at a scale of 1 in 2000, but once it's been scanned and then printed and downloaded and printed again, you may find that it's not at the original scale. So the first thing you need to do is basically exactly the same as you did in your contour assignment. Work out what's the scale of your plan. So there's a 100 metre bar scale that's printed on the plan, but there are then 3 other lines where data's been provided for you. the traverse lines, A to Y and Y to X, and also the distance from A to chainage 0, 0. And there's an example that's been given to you there where you can see the four scales come out, one in 1970, one in 1979, 1983, and one in 2000. So if you average the first three, saying, well, they're the longer lines, I might trust them more than the shorter line, that'll come to 1977. If you average all four, it'll be 1983. So there's not much difference there. So we're going to say, all right, I'm going to work on the scale of 1 into 1980. And whenever I scale a distance off the map, that's the scale I'll use. Now, look, for convenience and for logic, just always round your scale off to the nearest 10 units. Do not use 1977 or 1983. Always round it off to the nearest 10. Now, you've got to remember that the scale distances are only going to be precise to the metre or two. So if you do get some large differences in the scale, you might decide to reject 1 or 2. So one of the things you'll want to do is when you nominate what scale you've used, you'll need to tell us why you've made that decision. Okay, so looking back, the next thing you need to do is to determine the lengths of each of the three straights. If your plan printed true to the original scale, you could work with a 1 in 2000 scale. And so on the example I've given here, you can see the distance is sort of between about 140, it might be 141, and it might just be 142. It's definitely not 139, it's definitely not 143. So this is something that you, as the engineer, need to make the decision. You can say, I'm going to make it 140 or 141 metres. Your choice. What you've got to remember, though, is that the road needs to have its total length precise to 2 decimal places. So if you decide that the length is going to be 141, then it's going to be 141.000 metres. So this is to clarify the comment in the plan, or in the instructions, where it says, using your plan, find the bearings and distances of each of the three straights. Quote your answers to the nearest metre and nearest degree and adopt these values as being fixed for each straight. So in other words, each straight must always be exactly 1 metre long. So it can be 140.000 or 141.000 to make life easy for yourself. You're the engineer. As we said, if it's half a metre either way at the farmer's place, he's not going to worry. So make life easy for yourself. Work as 140.000, or if you prefer, 141.000. Now, if your plan's been printed to an odd scale, measure the distance in millimetres, multiply by the scale factor, but don't get carried away with the calculator. Just because you've got a calculator and it's got an odd distance and you're using millimetres, and you might get a number that says, in this case, 219.78. Forget that. Just round it off and call it 220.000. Because using a scale to millimetres at the scale of 1 in 1980, you can't get a precision down to the centimetre, even the 10th of the metre. And it's your decision. So remember, at this scale, 0.5 millimetres on the plan represents a metre on the ground. So the scale of this red line you would decide as being 220.000. I hope that's clear. That is an essential part of the assignment. If you round it off and produce some other number, we're probably going to mark you wrong, because if we don't know that you have decided to use 219.xxy and you don't, we won't know. We'll just assume that the rest of your information's wrong. Similarly with the bearings, you need to find the bearings of those three straights. If you haven't got a protractor, just go to the internet, cut one out, work with that. So you can adopt Tucker's Road as being your azimuth, measure the first bearing directly from that. After that, I find it's easier to measure the deflection angle. Put the bearing at the intersection point. What you do with a theodolite if you're out in the field. You'd set up at the IP, turn off the angle and measure the angle, and then calculate the bearing. Again, work to the nearest degree for these bearings. Don't try and get fancy with half degrees. Make life simple. As you see at the farmhouse, if you're a metre out, it's not going to worry the farmer. So make life easy for yourself. Work to the nearest metre, the nearest degree in all your bearings. You've been given in your data a specific radius to use for each of the two horizontal curves. So the next step is calculate the bearings, the angles, then the curve elements, and find the changes of the TPs along the road. And we want you to plot each curve carefully onto your plan and show that, and particularly take care with marking off the tangent points, because later on having them plotted accurately will be very important to let you draw the long section. Okay, finding the total length of the road. Remember, the road goes around the arcs. So you must calculate up to the IP, then back to TP1 with the tangent distance. Use the arc distance to get round to TP2. Remember these from the horizontal alignment assignments. Apply the tangent distances and the lengths of the straights and work your way around. Getting the precise length of the end of the road is very important, because that will be critical in getting the final grade to make sure that your road finishes at the required RL. Okay, plotting the curve is important, as we've said, and the changes of the TPs and the end of the road must be precise to 2 decimal places. So, in your submission, you need to mark up your plan showing the bearing and the length IP to IP. Now, look, I've marked it up here, 220.00, 145.00. In practice, you can knock off the trailing zeros, so you can just show it as 220, 145 and 110, but I put that in there as a reminder that you must work precisely to that metre reading. It is going to be 220.000. Now the contours get a little bit cluttered, so you can write bearing on one side, distance on the other, or if you find a clear spot, write the two together side by side. As long as they're marked on the plan, that's all that matters. Okay, we're now wanting you to do the horizontal curve setting out data. You're going to have a survey party that will come out after you've done the paper design, and they'll set out, you'll ask them to set out the road for you so you can show the farmer where it's going to go. So each curve has to be set out at running changes of 10 metre intervals plus the first and last TP. So what that means is going to be points such as TP1, 130, 140, 150, however many points there are around that curve, then TP2. We'll also want you to mark out data to set out the crown of each curve. So this is going to be used by the survey party, so it's got to be suitable precision for setting out. So answers to 2 or 3 decimal places and single seconds. Don't go to 4 decimal places and don't go to fractions of a second. You will be marked down for that because it's not appropriate and can't be done anyway. All right, an example on curve set out data. So let's assume the radius is 35. The deflection angle we find is 40. So we've got the change of the TP. The next point to be pegged, of course, is back at the even running change is 210. the crown sits at 219.475. Then we'd have 220, 230 and TP2. Okay, well, as you know, you can go through, do the tabulas for the delta I's and the delta T's and the long chords, and then remember the mathematical check. The final delta T is 1959.59. That's as you get it on your calculator, that's fine. That is delta on 2. Now this checks a lot more than just your curves. If you've made a mathematical mistake with TP1 and TP2, sometimes it works out that students don't get that 1959.59 mathematical check at the end. And as well as telling you that your curve, your set out elements are correct, it also tells you that the changes of your TPs are correct. So if you don't get that, it might be worthwhile going back and checking your changes as well as your deflection angles. Okay, we now want the survey party to mark out the end of the road from point X. So this is like your Travis assignment. Calculate the coordinates of Y and X, calculate the coordinates of the end of the road, and then find mathematically the bearing and distance from X to the end. Do not scale this. It must be a mathematical calculation appropriate for setting out. Okay, the extra survey work. What do you want the survey party to do for you? Set out the curves, possibly do some long section work so you can get a better estimate of the long section over and above the contours. Think about how precise the contours might be. Might there be some extra data you want? Is there something you need confirmed or clarified? Please just confirm your comments to the centre line of the road. Obviously a road has width, but in this case we're not going to worry about what happens to the left or right hand side of the road. We're just looking along those 3 red lines. One final part of the assessment asks you to do some estimation of volumes between changes 10 and 70 on your road. Your data sheet gives you some RLs for the changes 10 to 70. Let's say the survey party started out there marking out the 10 metre intervals, got that section level, then heavy rain came in. So the paper design's been done. Don't use those levels for your long section. Long section's only drawn with the contours, but at least you've now got an estimate of what sort of volume is going to be involved in getting from change 10 down towards the creek cross to get change 70. So you'll need to transcribe your natural surface levels that are given to you and the road design RLs that you've calculated on your vertical curve table onto the volume sheet. Then you'll need to calculate the area of cut and fill. We've drawn typical cross sections for you so you can see the height. Your data sheet will give you the road formation width. Your batter slope will be given to you in your data sheet. And so one of the first steps will be using the height of cut or fill as calculated from your estimations, your work. Calculate the area at each of the cross sections and then work out the total volume between changes 10 and 70. In real life, and possibly in this assignment as well, despite your best intentions and attempts, it may not be possible to meet all the design right criteria or requests that the client wants. So what you've got to do is say, well, these criteria are more critical than others. I'll do my design on that, and then I'll have a chat with the client and say, well, here are some things which don't quite meet what you want. Can you live with that? So the criteria we're saying are going to be most critical that you'll have to adopt are the starting and finishing RLs of the road. The other one is the location and RL of the intersection point of your first vertical curve. So that grade is fixed. You can't change that. After that, we want you to do the design that climbs up the hill, goes over the crest and finishes at the end. Try and follow the natural surface, having balance of cut and fill. There's about an equal amount of cut and fill. You won't get it on the first grade. We've deliberately made that, but after the creek crossing, try and balance it out roughly. Avoid deep cuts and fills. If you can keep it within a metre, that's great. We'll let you go to 1.5 metres for short distances, but probably if it gets to 1.5 metres deep, you should be reporting that. For an access road, we want to keep closer to the surface. There are a couple of things that are critical to this assignment. The nominated horizontal curve radius must be used. You don't have free choice in that, as you would if you were a real engineer. After the first grade, which is fixed, has been adopted, you must then have no more than 4 new grades. So we'd suggest aim for 2 or 3 to climb, follow the natural surface to climb to the crest, and then just aim for 1 grade to come from the crest down to the finishing point. The other thing is all IPs of your vertical curves must always lie on an even 10 metre chainage. So in other words, 220, 230, 240, etc. And vertical curve lengths must be only 60, 80 or 100 metres long. This is just to make life easy for both you and also for us for marking. So vertical curve IPs at 10 metre chainages and only 60, 80 or 100 metres long. Okay, well hopefully this gives you some ideas as to what's involved. Keep this diagram in mind. You're designing this rural access road, so it's not a 3-lane highway or expressway. And try and think as an engineer would. We want you to experience what it's like making some design decisions and thinking through how a project would operate. Happy designing.